All right, so it's.
Okay, Nico.
Awesome. So we see quite a number of attendees joining. Thank you for your patience. We were working out some technical issues behind in the background here. Give us just another few minutes, 2 or 3, and we'll see as folk join and as that number starts to slow down a bit. I'll kick off with some introductions, some sort of ground rules, and we'll move from there. But welcome, happy 12th of May. And we look forward to kicking off in just a moment. So hang out with us for just a few minutes while we get ready. And if you haven't attended a ClickHouse release session in the past, one of the things that Alexey does that I love deeply is to welcome people from the community that he recognizes. For those ClickHouse folk on the call, Nick, Pascal, Alyssa, others, welcome. We are delighted that you are here. I see a Dan Palmer. DPP, what's up, mate? Welcome. Very excited to see you here. Stefan, also great to see you. Thierry, Thomas, it's exciting to see all of the folk come in. Hang out with us for just another minute or two while we pull things together and get ready to kick off today.
I see 5 instances of Elisa.
Yeah, I saw that. I think it's because I shared my direct link.
Perfect.
Yeah.
Awesome, and it looks like people are continuing to join, but in the interest of time, I'm gonna go ahead and get started with just a welcome and some ground rules. So, hey everyone, welcome. This is exciting because this is a ClickHouse meetup virtually across a variety of geographies. So whether you registered for this meetup via London or the Netherlands or France or Munich or Berlin or Bangalore, welcome. We're excited that you're here. My name's Tyler. I look after DevRel at ClickHouse. I'm super excited today because today is not only a meetup where we share a story about what we care about, but we start with users telling their story. And I am super delighted to be able to welcome Guillaume Coffin and Guillaume Aubert from Opensee to join us. We're going to spend about 45 minutes hearing about their story as well as their architecture and technology. Leave a little bit of time for Q&A. And then we'll hand it off to Alexey. Alexey, if you don't know, is the CTO and co-founder of ClickHouse. I have had a preview into today's slides, and I am delighted with what has been prepared for us. We'll save a bit of time for Q&A at the end, and then we'll wrap up. So over the next 90 minutes or so, you'll see that you have the opportunity to raise your hand, that you can use the chat window. Please do use them. Please do use them liberally. And we are excited to kick off. So with that said, I am delighted and I'm honored, honestly, to welcome the folk from Opensee to share their story with us, not only of their business, but of their implementation of ClickHouse. So with that said, Guillaume, would you like to take it away? I think you're muted, mate.
My mistake.
Yeah, thank you very much, Tyler. So I'm Guillaume Aubert. I will present the first part of today's meeting. So I'm going to share the screen. Give me 1 sec. Okay, can you see my screen, everyone?
Yeah.
Indeed, we can.
Yeah, we're all good. All right. So I'm a Chief Product Officer at Opensee, and in that first presentation, I'm gonna present what the Opensee can offer to the financial community, financial industry. And then in the second part of the presentation, under Guillaume Coffin, head of engineering, we get into a bit more technical details on how we've implemented and connected ClickHouse as part of our platform and solution. We're gonna see three angles in that first presentation. High level, what kind of problems we are solving for financial institution. Some highlights on functionalities that we provide. And then we're gonna finish on the typical use cases, business cases that we address for our clients and that we have actually implemented and live for our clients. So very high level, what do we do? In a nutshell, we offer a big data analytical solution for financial institutions. What does it mean? Banks and financial institutions in general that are sitting on top of hundreds of terabytes, sometimes more of data of any kind, market data, trade data, risk data, sometimes, not always, but sometimes stored in a data lake in a very unstructured way, sometimes difficult to join and to get manipulated together. And then the bank, for different reasons, either business needs or regulatory requirement, they need to extract values for the users from this data to create some risk optimization reports, advanced trading decision. That's on the business needs side, and for regulatory requirement, they need to compute, report capital charges and understanding on what are the drivers for these capital charges in order to optimize it and so on. No need to say that if a bank is unable to get into this level of providing this business needs or requirement, they are exposed to some pain points, loss of business opportunities and even worse, some compliance breach when it comes to regulatory requirements. So here we're talking about a very important topic for banks. Just one word on the kind of landscape of system that we've found on that market when we started a couple of years ago, and how we position ourselves today. So on the right side of the triangle here, you see what we call a standard databases. So that's probably one of the first offering to address this requirement. This kind of solution, they have to deal between a trade-off in terms of speed versus data volume, and very often in order to achieve enough speed, they have to compromise on the data, and especially on data accuracy, and they need to pre-aggregate the data. So they are kind of suffering from this kind of limitation. Then we go to the left side of the triangle. You find some solutions which are called themselves data lake accelerator or extended Hadoop stack. And what they offer is a layer that is sitting in between the end user, let's say BI tool, business intelligence tool, and the data lake, and helping to structure the data and providing indices, aggregation, pre-aggregation, so that the end user can on the fly access the data. So here we are trade-off to find here between the autonomy that it provides to the end user versus the speed, and very difficult to provide both at the same time, given kind of the complexity of the layer that is sitting in between with some Spark engine and so on and so on. And then the third solution that we found, systems, or memory solution. The approach is to take a slice of the data, like a snapshot of the data from let's say data lake, and let the user interact directly in memory. So of course it's fast, but then this solution are hitting a kind of a limitation, a bottleneck, in the sense that it's very expensive because the data is held in memory, and when you reach multiple terabytes of data, it may be very expensive. So our positioning here is to try to achieve all three goals at the same time: cost efficiency, speed, autonomy, and by keeping accuracy and depth in terms of data management, all at the same time without compromise. And that's the platform and then solution we've built on top of ClickHouse. So I'm gonna just present very high level, of course, that architecture and then Guillaume will Coffin will get into more detail. But here, this is the functional architecture, I should say, of our product. At the bottom level, we have the ClickHouse database. So this is used for storage of data in a structured way and to run some low-level aggregation of the data, super fast and super scalable, and as we all know, and then Guillaume Coffin will come back into some details. On top of that, we've built lots of functionalities, which I will detail a little bit in the next slide, but basically to help user to access easily the data or the bank to deploy the solution in like a one-click approach. We get into more detail on functionality. So that's what we call the platform within Opensee. And on top of that, we've learned and we've implemented some specific business cases, use cases with our clients in the last 2 to 3 years. And then we've learned, what's the best way to model it, to implement this with our data metrics for these specific use cases. And I will present at the end of that first presentation how we've actually structured the data and manipulate the data to achieve the goals for this various business requirement. Functionality-wise, this is again very high level. I'm gonna highlight a few points. On the data aggregation angle, the most important aspect is that we provide a abstraction feature, abstraction layer between the user, the way the user interacts with the data, whether it's from the UI or using API, and the actual physical model in ClickHouse, whether it's we store like data using a star model, using arrays, and all of the features you can think about in the database. This is completely abstracted from the end user that doesn't need to know the complexity behind the scene, and then he can then build this query very easily as if it was represented as a kind of flat data model behind the scene. Just an example here of functionality which is quite important and that we will detail in a second. There is important aspect of data ingestion because you need to get data in, of course. So we've built some massive volume data ingestion API to be able to get terabytes of data on a daily basis and in a timely manner. User needs to interact in and out with the data where they need, for instance, to adjust some data either for simulation purposes, see the impact of value change on that particular record, or adjust the data just because the data was erroneous and it needs to be adjusted. So there are all of functionality for data adjustment which are very important, which we've built in our platform. We are providing as well some UI, user interface, either like application desktop or a web interface. And we also let our clients plug their own UI if they want with the API. Again, last but not least, on this overview is all of the features that are required for the integration of the system in the financial institution infrastructure, because the cluster has to be sometimes on the prem, sometimes on a cloud, sometimes on a hybrid situation. There are tools which is this deployment which needs to be used, such as Kubernetes. So this is some integration work that we've done and that helped the bank deploy our platform. So that's kind of complete the functional part. Again, very high level. And now I'd like to jump into a description of the actual use cases we have solved for the banks. And I'm going to focus here on one particular area, which is of interest for us. It's risk management. But there are many more areas for financial institutions where we are involved. There are some transaction management, execution prices, and market data management. So, if you're interested in this use case, you can come to us. But I will just focus on some risk management, which are probably easier to understand. So the first one is I want to focus is market risk. So what is market risk? Because I'm not sure everyone is familiar with finance here. Market risk is a domain of risk management that will try to assess what is the potential loss on a portfolio given some market changes, market data changes being foreign exchange, equity prices, interest rates, and so on and so on. And very often the financial institution, they will look backward, they will look at historical data to be able to predict future changes of this market data and anticipate this potential loss. So here we have a methodology which is called historical VARs, very known in the financial industry. And the principle is the bank in their pricing engine, they will run every trade of their portfolio through some historical scenarios, meaning that they will look at the changes in market data in the past, apply this market data change on current market condition, and rerun the value of that portfolio to get some we call P&L impact, profit and loss impact, or change in value on every trade for every scenarios. So here we end up with what we call the data sets for market risk, and here it's of course very conceptual. You have all of the trades in one dimension, and you have some number of scenarios in the other dimension, and this can go up to, let's say, 10 years in terms of number of scenarios. So we end up with 2,500 scenarios here. So that is data sets, and then in addition, the financial institution they will provide some enrichment on the data in terms of the attributes of the trades regarding the counterparties, or regarding the portfolio structure of the trade belong, regarding any kind of information that is necessary to enrich the trade and to build the reporting after that. So that's kind of the blue block, which is right below the Opensee square. Based on this data, Opensee, leveraging ClickHouse, will be able to generate all of the useful metrics for market risk management. So the most famous one is VAR, value at risk. And once you've got these scenarios, you will just have to aggregate scenarios according to some aggregation level, which could be, let's say, books, desk, or whatever portfolio level, and take a quantile. Typically, could be a 1% or 5% worse scenario out of this whatever you need for your calculation. So that will be the VAR, and then we can derive some of our important metrics. There will be a marginal VAR. Marginal impact will be what is the VAR change if I exclude one specific, let's say, book or desk from my calculation. Okay, keep in mind that these calculations are non-linear, so you don't just add up and to get some intermediary number. You need to do some specific techniques if you want to get some marginal calculation, and this is one of them. There are some other derived calculation, stress period, which is very important, where here I'm considering an history of 10 years. The VAR is typically computed using a 1-year history. And then the financial institution is going to look for the worst kind of 1-year period within this 10-year in terms of the VAR. So the highest VAR number, that they call it the stressed VAR. So the VAR for stress period. And so on. And then there are some regulatory capital metrics which can be derived using the same kind of market data. So it's a very rich and important data set for everything which is on the market risk side. Another domain of risk management is credit risk, and specifically the credit counterparty risk. What is it? That describes the potential loss that a bank can have or financial institution can face if there is a default on a specific counterparty. Okay, and this is the case when the portfolio that this bank holds with that counterparty has a positive value, right? Because this is when the counterparty will have to give them back some money, and if they default, obviously that will result into a loss for the financial institution. So here we're going to look at something which we call the positive value of the portfolio with respect to any counterparty. That would be the kind of the base number. So how do we get there? Here again, the bank will typically run a simulation. So they will simulate, again, for every transaction, every trade, the value of that trade according to number of scenarios in order to build some distribution. Here, because in general, the confidence interval they are looking for is tighter than the one in market risk. They will need a much higher number of scenarios. And usually the method which is used then is a Monte Carlo simulation, because here you can go up to millions of scenarios or any number. You're not limited by the depth of your historical data. That's probably the first difference compared to market risk. So all of the scenarios are randomly generated according to some laws which are described by history, but at the end it's a random scenario simulation. That's the first difference. The second difference is that the counterparty risk is an exposure that the bank will hold very long time in the future going forward. They will not, unless there's special events, they will not cease the relationship with the clients. So they will need to be prepared to hold that relationship and that exposure very long in the future. So we need to project the value of the portfolio forward at any point in time, from very short term to up to 50 years, for instance. So here we have this horizon date dimension, which comes in addition to what we had before in market risk, which is focused more on short-term change in value. And we end up with this kind of data sets. Okay, so horizon dates, scenarios, and trade dimension in rows here. And here, same story. The financial institution that you're gonna use our system to compute the usual metrics, very important metrics. So there are some which are called expected exposure. So that will be the average of the positive value of the aggregated by counterparty. So that's the EPE, expected positive exposure. That's the base kind of number for risk assessment. And then there are also, in the same spirit, they may compute a quantile rather than an expected value. This is called potential future exposure here. And then this is used in the financial institution to set some trading limits in the trading room. That's what is used to say, okay, trader, you're not allowed to trade more than X million against that counterparty. So you see there is direct usage by business. And then there are some situations where you want to assess what will be the impact on my loss, potential loss, if there is a specific macroeconomic events or specific political events in a country on my counterparty risk. And then you will have to roll up the exposure for all counterparty that are in a specific country and industry. So this is also a typical functionality. Again, this is nothing but a linear calculation. So every time you need to kind of rerun on-the-fly calculation from your raw data to assess this kind of metrics. And here again, in the counterparty risk side, you've got some regulatory metrics that we are also capable to compute in the same spirit. I don't know how we're doing timing-wise, Tyler. We didn't check the time, but we're doing good.
We're okay. Yeah, we're getting close to the 20 minutes that we've set aside. But
if we want to kind of cover the full spectrum of risk management, liquidity risk is I would say is the last one in the main risk category, and this is where the bank needs to assess their ability to pay all of their obligation in terms of cash flow in the future, because if they are not able to pay their obligation, they will default, right? They will be in default of payment, and this is what they are trying to avoid and to assess. So that's what the liquidity risk is doing here. The data sets, again, we are talking about conceptual data modeling, of course. The data sets will consist in projected cash flows, so payable, receivable by the financial institution at the level of every trade. and according to some time bucket in the future, because we are interested in what's going on in the future. So from short-term to long-term time buckets. And in addition, they will have to run some scenarios as well here, which could be either market scenarios, because you may have some floating rate instruments, floating rate loan, for instance, and then the cash flow will be impacted by the level of interest rates. Or you could have some behavioral scenarios where you want to make assumption about how the borrowers will prepay their loans, for instance, or how the cash account holder will close or keep their cash accounts open. I mean, all of this needs to be modeled as assumption, and it will, of course, change the liquidity profile of the bank. So we end up with this kind of data sets that then, again, the bank will implement with our system some specific metrics to assess that liquidity exposure. And there are typically two categories here. One is on the short term, and it's usually called the cash flow gaps or cash flow mismatch. They will really look on the short term, and let's say first week or first 30 days, and make sure that there are always kind of positive cash, or if there are negative cash flow, make sure they have ability to fund easily overnight this negative position. That's the first aspect. And then on the medium to long term, there are different techniques, but then again using same kind of data, which are called asset liability gaps, where the bank will make sure that we will be able to finance with liabilities all of their assets, assuming that their ability to finance depend on the quality of their assets that they will put as a collateral of their liability, and so on. So there are some categorization of these assets that you need to take into account when it comes to medium-term to long-term financing. I think I'm going to stop here because I'm running out of time. But I just wanted to give you some ideas of use cases that we've implemented for our clients. As I said, there are many more in some area which are not risk management, could be trade management, market data management, as well for buy-side institutions. Before I hand over to Guillaume, I wanted to show you like a quick demo of the system using our UI, desktop UI, just to show you the system in action. And I'm going to launch it while I'm speaking here. So do you have any music or not at all? Maybe not.
No, we do have a bit of the music coming through, but it's relatively quiet. So I think it just went off. So yeah.
So here we go. I think I'm going to hand over to Guillaume now for the second part of the presentation. And I'm going to control on sharing, is that right?
Yeah, you need to stop sharing, please.
Thank you. Try to share.
I can't unless you stop sharing.
No.
While we figure that out, I'll monologue over top of it. It's wildly intriguing. You know, fintech is not a domain of expertise of mine, but even looking at the concept of trades times buckets times scenarios times valuation dates, and realizing how quickly that data set gets big and complex, and giving people the ability to drill down into that is super compelling. Like, there is a lot of angles where that data can be looked at, but it's intensely critical for the business as well, which is, it's just exciting. And Guillaume, just so you know, we're able to see the slides now, so we should be good.
Okay, thank you. So I'm Guillaume Coffin. I'm the VP for Opensee. I'm going to give you a quick overlook of the technical architecture and how we manage to do the software that you've just seen and manage all the data behind it. I'm going to talk quickly about the challenges, why do we need such an architecture, and then go a little bit in the details of the architecture, and then discuss current issues and the way forward. So when the development was started, the idea was to address those four main challenges. Of course, there are many more, but the first one being, as you saw, how to be able to quickly dive into the data, do very fast aggregation and filtering. So that means two things. One is to create the proper queries that will run very fast and such large amounts of data. And that means to have also the physical data model that goes with it. And the second one is to have a fast response, which means not only the query that runs very quickly, but also includes everything else, such as building the query and serializing the data very quickly. The second challenge is the distribution, the amount of data you've seen. We're talking about billions or hundreds of billions of lines. So that means that the data cannot fit on one single server. It has to be distributed. And also the computation has to be distributed, not only on the ClickHouse side, but also on the backend, and for also for reasons of high availability. The next one is to run user-defined functions in Python. So ClickHouse doesn't allow that, as you know. So we wanted to have a system which also can be distributed, runs on pre-aggregated data, and can do all sorts of calculations. So you saw the value at risk, which is one. The idea behind it also was to provide with our clients with a language that is quite common, that they can develop and find developers within their workforce. And the second idea is to provide them with a nice development environment where they can debug and test also quite easily. And the last one is, well, we have customers, they want to have sometimes their data on their own infrastructure. So we need to be able to distribute, to deploy on-prem or on the cloud. So the main functions that Guillaume has shown, well, to achieve that, I'm going to focus on three main ones. The first one is the ingestion. That's critical for us. The data is copied inside Opensee because, first of all, we have our own physical data model to address everything you've seen, to address the scenarios, the various versions. We need to have our own physical data model. And also the query speed being so important. So we need to manage really that very closely. At ingestion time, we do some pre-calculation when required, either because we need to fit to that physical data model, or because we do some optimization, for instance, pre-aggregate some data. So when it's required, if the data or that is pre-aggregated already exists, then that's the one that the engine we choose. Otherwise, we keep always the most granular data. And the last one is the applicative transaction ingestion. We want to make sure that our client, they have the version that they want to. So it means that if you ingest data, and if they run analytics at the same time, you don't want them to have report that would take into account only half of the data, that was ingested because it's still going on. We need to be very clear. So that's why we have such a strict versioning system. We always know what version they are. Well, the user always know what version they are querying, and unless the ingestion is complete and successful, they won't have access to the newest data. The second function is obviously the query. We have our own query language. It's actually a REST interface with Json. It's a pretty simple where you can define typically how you aggregate the group by and the where clause and so on and so forth. We also provide an Excel interface. And all of that has to be somehow transformed into SQL that is understandable by ClickHouse. And that's the role of the core engine that I'm going to present later. And the last part is the data management, also a very important part. We talked about the versioning. The versioning that we provide is basically based on the concept of code versioning, such as Git, where you can manage your branches, your commits, and everything. So it's not Git actually, right? It's encoded on ClickHouse, but it's a similar system in terms of functionality, and it allows to. It's a very powerful system to run validation workflows, to be able to compare between scenarios and versions, to do data adjustment, and so on and so forth. So here's the overall view of the architecture. The core of it is backend written in Scala. It provides all the interface with ClickHouse, where all the big data is stored. We also have a PostgreSQL database for everything that is transactional, and relational. Also, as I mentioned, we use Python in a distributed calculators, where the data frames are stored with Pandas data frame. We have two types of, actually three types of front end. The one which is written in .NET, it's a desktop application. Another one which is for web access, and a third one which is actually developed by our customers, and they use the REST API. So if we take an example of a user that would want to check to do some analytics, the user would connect to the user interface. Let's say the web interface. So there's a TypeScript written Angular application, and just by clicking on a button, that would trigger a call to the Opensee API. The Opensee API will receive that request, which is actually the Opensee language request. Is going to call an engine that converts it into a query plan. Potentially, it will build all the SQL queries, potentially called directly ClickHouse, or call Python calculators in a distributed fashion that will in turn call ClickHouse if there is a need for post-processing. Then the Python calculator calls the UDF that was developed by the client, and all the data is streamed back to the Opensee API and then to the user. So that's the sequence of events, and it relies a lot on the Opensee core engine. So that's the core engine. What does it do? It's a component that uses on one side it bridges the conceptual data model as seen by the user with the Opensee features that we add on top of it. For instance, the facets, the versioning, the fact that we have arrays in the data. And it bridges it with the ClickHouse physical model and creates the query. So how does it work? It takes the the query from the user. It compiles it, generates a relational algebra, enriches it with the Opensee features, embeds the Python distribution if need be. There is some optimization here, and then generates the SQL that is run directly on the ClickHouse database. So it's essential for our customers that we have a very good performance, because if it's too slow, then the whole interaction with the software is going to be difficult and non-fluid. So in order to do that, we use lots of features that ClickHouse provides, such as nested arrays, the vectorization, in-memory dictionaries to do joins when needed and enrich the data, facets. So facets are those, it's actually materialized view run on some of the fact table when we need aggregation, when we have aggregation that are used very commonly by the queries run by the users. Now we think that with projections, we have a good opportunity to improve that further. And there are other specific features, and just mentioning one, using unique exact instead of counting, that's very efficient and for the same result. And we saw great improvements. We chose ClickHouse 3 or 4 years ago based on benchmarks, and it really showed matched performances for all our use cases. And so we continued, of course, with ClickHouse. A few words about deployment. We deploy on Kubernetes or bare metal, as I mentioned. Here is an example of Kubernetes deployment with several pods running Python calculators. We use a ClickHouse operator to deploy the ClickHouse pods. Always replication, so Postgres also is replicated. And the Opensee API server can be, so here we have only one instance, but there could be as many as we would need. So the typical issues that we encountered in the recent times are typically first the zookeeper, because we deploy at our customers in our customers' infrastructure, we don't control everything, and we had regularly issues. Typically with the configuration, changing infrastructure sometimes, timeouts, and so on. So we have a plan to use ClickHouse Keeper. We haven't had a chance to do that so far for now, but that's clearly something that we are very excited about. The second issue we commonly have is about the joins. We need to join with very large tables. Sometimes it doesn't fit in memory. So we either find other ways, or but the memory improvement is something on which we have to work. Another way to manage that is to denormalize and copy all that data into table and disk, which is efficient from a query point of view, but of course requires much more space, especially when the data is highly redundant. And the last one is the ingestion. We found out that there are many hyperparameters to tune. It's hard to understand what are the bottlenecks between the CPU, disk speed, network, and what we found ways to manage, but that's another one where typically it can be difficult. So the plans for us, lots of things to develop on the product side. Here I'm going to focus on what we want to do on the technical side. First of all, the first thing is because performance is so important, we need to further optimize our queries. Typically to have a data set, there are several ways to write your queries, and that's the role of the engine that I presented. So how to write it in a way that is most efficient. That's an interesting and quite theoretical domain that we address. The second one is to be able to transform the data before loading. For now, we don't do that. We expect our customers to do it. Actually, no, we do a little bit of it with materialized view, but that is also something important when we want to integrate with new customers, and that's an area that we need to cover. I talked about resource footprint. That's something on which we work. The ingestion also, I mentioned it. And the last one, which is something we are only starting to investigate, is to provide some mutability. That's something we didn't have to do because we had this versioning system. But what if we don't need to have version system and only the latest version is useful? then it's quite a space saver on disk. And so we need mutability to do that, which is a domain in itself to make sure that you know exactly what data is actually currently queried. So that's it for me. Thanks for your attention. As you can see, plenty of interesting domains. So we're still hiring, by the way. So if you're interested and based in Paris, don't hesitate to contact us. Thank you.
Guillaume, thank you so much, both of you. There was a question that I'm going to ask because it came up and we've got a couple of minutes. And feel free to answer to the level you're comfortable, which is, hi, you said joins don't fit in memory. May I ask how much memory you have in your shards?
Well, typically, the maximum memory which our client will have on our cluster server will be 128 gigabytes. They will probably go to 256 if they have no other choice, and there is no other solution for them to avoid the problem. But they barely go. I mean, they usually stay at 128.
And the idea is, as Guillaume mentioned during his presentation, is we don't want to have too costly infrastructure because we can usually manage with much less memory. It's only when we have very large decoration to do, which is something we want to avoid.
Yeah, sort of the collision of a large data set. Yeah, it makes sense. The person who asked says thanks a lot, by the way. Another question was, could you tell us a little bit more about how you work with data versioning? I actually think that's a really interesting problem space that you described, the sort of notion of versioning and then looking at expanding that sort of strict versioning into more of a mutable construct. Yeah, what lessons have you learned there, or what tips would you love to share with people who are watching this either now or in the future?
Well, probably don't want to give too many details here because this is we have something which is a bit kind of in-house techniques.
Yeah, fully.
What probably is important to mention, it was inspired by kind of versioning system that your guys are probably familiar with in Git, where the data is or adjustment or structure as the form, using some specific commits. And bringing that data together will be based on merge and rebase and so on. So we've built a whole system on data, which is actually was existing before on sources for programming. So I think it's been quite innovative. And so it gives a lot of flexibility for user to track changes. To go back in time, to take this change and apply this change together. So you see the universe of capabilities that it may offer.
I think a great thing about it is that the data is you only add data, and that's really great because especially in systems like ClickHouse, you don't want to change the data, and so you have much more control on the data integrity.
Yeah, totally. In a prior life, I spent some time with a company called Fauna, and FaunaDB has the concept of temporality built into sort of OLTP style model, and that sort of notion of versioning is relatively niche, but when needed is deeply important, right? Like it's absolutely necessary when it's absolutely necessary. I find it a wildly intriguing sort of area of study. We've got 2 more questions. I'll just ask them real quick because I know Alexey won't be mad. How did you work out OLAP queries with ClickHouse? Was there built-in support in ClickHouse, or did you do it outside of ClickHouse? How did you think about OLAP and ClickHouse?
So everything that is OLAP, I'm not exactly sure to understand your question. So all the queries actually built by our core engine, and basically it calls the queries and aggregation inside ClickHouse. I'm not exactly sure.
Nah, I think that's actually a perfectly fair answer. And you talked about the sort of layer of and it's actually what the next question speaks to a little bit. You talked about the layer of API that you provide above. And that's actually what the next question gets to, which is like, you know, was there something in particular that sort of motivated the need for a separate language sort of via REST, like the Opensee language versus native SQL? Is it domain specific, or was there an element there that was like, yeah, we need to build a thing?
No, actually, there are OLAP languages. You can think of XMLA or a DMX language. We actually implemented that. It's just that this version, the Opensee language, is just a simplified version, very easy to build. That's it.
That totally makes sense. You're minimizing the overhead of interacting with the data on behalf of that financial institution by giving them something that they can interact with well. Yeah, and someone typed in chat, it's the abstraction layer. That's the phrase that I had lost.
Key factor was to provide direct access to for the end user.
Yeah.
Okay, so you need to have an API which is as simple as possible, and that's what we call the abstraction layer, where everything is looked at as if it was like a flat data model, whatever the actual physical model is behind the scene. And we got a feedback from our client that it's actually much easier to use than XMLA or MDX, if you're familiar with the language, which is used to be a standard as well.
Yeah, it totally makes sense. Well, excellent, folks. Thank you immensely for your time. Thank you for sharing sort of your history, what you do, and importantly, how you do it. There was a moment there in the slides where you're like, hey, we chose ClickHouse because of benchmarks. And that makes my heart warm, particularly since Alexey, who's speaking next, is talking about the way that we view speed at ClickHouse from a product perspective. So with that, Alexey, would you mind taking it away?
Sure. Let me share my screen. Okay, I hope you see it.
We do indeed.
So I will try to answer a question, why ClickHouse is fast. But this question is very difficult to answer because there is no single answer. There is no single secret inside ClickHouse why it is fast. And as it's difficult to answer, instead, I will just do some hand waving. I will just show you some random principles, ideas, and facts. So, how to write a fast database? If you want to write a fast database, or if you want to write something that as fast as ClickHouse, even faster as ClickHouse, how to approach this task? The first idea is just to use the best algorithms. But there is a problem. There is no such thing as the best algorithms. Let me show you one example. So you want to write a database management system and you want to make it fast. You can approach it this way. Okay, I will write code in fast programming language, C++, or maybe C. What is faster, C++ or C? Or I will use Rust. It is as fast as C++, but even more modern. Or maybe should I write it in assembly language? It will be fast. I will use the best libraries. If I need to parse Json, I will use a Json. It is the fastest library. I will use Apache Arrow to manage column-oriented data in memory. It should be fast. I will manage data with memory mapped files. Or maybe should I use in-memory database? ClickHouse is not an in-memory database, and you know that memory is faster than disk. So I will write it like in-memory database, and it will be faster than ClickHouse. I will use asynchronous framework because you know what, asynchronous is faster. Okay, this is really a bad idea, and let me explain why. So let's start with one isolated example, parsing and processing JSON data. You know that the fastest library to parse JSON is SymdJSON by Daniel Lemire. Look at his face to the right. This guy cannot be wrong. He has written the fastest JSON parsing library, and he is responsible for that. So ClickHouse is using this library, and there is a benchmark, very recent benchmark, named the fastest command line tools for querying large JSON datasets. It is comparing JQ, DSQ, TRD SQL, Spark SQL, Miller SpyQL, OctoSQL, and ClickHouse. And the best performance, not surprisingly, is shown by ClickHouse and also OctoSQL. And ClickHouse is using SymdJSON. So obviously, it should be the reason for the best performance. But it is not. It is not the reason. Yes, ClickHouse is using SymdJSON. Yes, SymdJSON is the best library for parsing JSONs. But ClickHouse is not using SymdJSON in this particular context of parsing input data. So the question is, does ClickHouse even beat SymdJSON in performance? And the answer is, it's complicated. So ClickHouse and OctoSQL are faster on JSON processing, but not because they use SymdJSON. Because they don't actually parse JSONs in a generic way. Instead, we do the following. We parse first records, like 1,000 of first records. We learn the data structure from this. And we expect that this structure will be uniform across all the data set. And we use this learned structure inside JSON to do more specialized and structured parsing. And it appears to be even faster than using the fastest generic JSON parsing library. You know, there is one Chinese poetry saying that if you want to parse JSON faster, probably you don't need to parse JSON at all. Okay, let's continue. So every algorithm makes sense and makes different sense in different contexts. And you should take care how exactly every algorithm is applied. Let's take my favorite algorithm, hashing, hash functions. I love hash functions. And I love fast hash functions. But it is very difficult to choose the best, the fastest hash function. Every year appears a new blog post from a new author saying that I have written a new hash function, and it is the fastest hash function. If you will search on the internet, you will find that Wang-Yu hash is the fastest quality hash function. What does it mean? XX hash from Jan Colette is extremely fast hash algorithm. Maybe it is even better than Wang-Yu hash or Aqua hash. Fast hashing, just fast hashing, but at least they have some diagrams. Okay, it is difficult to choose, but the question you have to ask yourself, how you are going to use this hash function? Maybe you will use it inside your hash tables, maybe in hyperlog data structure. No doubt you know what hyperlog is. I will not tell you. Or maybe you want to just expose this hash function as a function in a SQL language. So the user will write something like select my best and my fast hash function from table. But there is a paradox. If you expose this good hash function in SQL language, you cannot longer use it for hash functions or for hyperlog. Because let this function exist in SQL. Then your users may write something like this. To distribute data or to partition data by the value of this hash function, because the users will know it is fast, so why don't use it? And they will use it. And the data will be partitioned by this hash function. But if you write a query like select group by X, or select a distinct X, or select join on X, these queries will be surprisingly slow. Because on every server, on every partition, the low bits of this hash function will be identical. And this query will waste memory, and data structure will work slower. So the problem, you put your best hash function in one place, and it will work fast. But you cannot put it in another place because it will work slower. One context of application changes another context of application. It is named interference of hash functions. So it is not so easy. Not so easy to simply use the best algorithms. How to test hash function? How the author tested it? Typical mistake will be just to test on random data with the same length. Say, I will just make a loop on a strings of length 10. Better developers test on every data size and draw some charts, diagrams, and compare on every data size. So I will compare my hash function on size 2 bytes, 3 bytes, 10 bytes, 100 bytes. And my hash function should be the best on every data size. But then you can make another mistake. If you will write a loop on strings with some data size, like 10 bytes, even if you test on every data size, you still should not forget to test on different distribution of data sizes in the same loop. Because if the size will be the same on every loop iteration, then CPU branch prediction will work too good comparing to production workload. And on production workload, this hash function can be slower, but you still have to test it. What if, like in production, 90% of strings are empty and 1% of strings are longer than 1 kilobyte? Okay, I will not dig into this detail, but I have to dig into details, and you have always to dig into details if you want to to build for fast. Let me also provide you one example. How many times there was a situation when you open some website and this website is loading 1, 2, 3, 4, 5 seconds, and it is quite annoying. You think it's a bad website. Let me check it once again. You hit refresh button and it is loading instantly. You hit refresh 10 times more, it is loading instantly. And you can come to a conclusion, it's just a temporary glitch. I don't care. It does not reproduce. If you will go and write to support that I have loaded your website, it has loaded in 5 seconds, the support will answer, your problem does not reproduce. Probably it is already fixed. Why even bother? And thank you for using our service. But this is wrong. The right approach will be to ask a question. Why this my particular request processed slowly? I don't care about million other requests to this website that are processed quickly. I only care about this particular request. I want to find it in the logs. And I want to find detailed diagnostic. How much time spent for querying MySQL? Did it really make 100 queries to MySQL and 200 queries to MongoDB just to show the landing page? And to optimize it, in ClickHouse, it looks like this. We run some benchmark. Most of the time, it is all right. Here I compared performance of ClickHouse on local file system and performance of ClickHouse on S3. Most of the time, S3 is not slower than local file system. Not slower than 2 times. But sometimes there are some glitches. Like one query is processing half a second, and 10 times more, just half a second. But 1 out of 100 times, it will process in 20 seconds. It is unbearable. I cannot stand it. But every time, this is different query. I have to figure out what is this query and why this particular query spent so much time and where did it spend so much time. Happily, I have all the diagnostics in ClickHouse. I have the system query log table, and I can see all the metrics related to every single query. I can compare one query to another. I can aggregate and compare different query classes. I can compare resource usage by different users. But for this example, the reason of slowdown was very obvious and not surprising at all. The query was slow because it had to read 2 gigabytes of data from disk. And on this particular server, this disk was slow. It was small EBS volume on Amazon. And this reading took 357 seconds if I summarize across all the threads. Nothing interesting. What do we have inside ClickHouse to provide this diagnostic? we have always on profiling. It is profiling that is always on. Yes, you also have this profiling on your server. It is aggregating data. Even if you don't use this data, it is collected. And if some query processed slowly 1 month ago, you can do this query from system trace log and figure out where the query spent most of the time. You can even aggregate this data across the cluster, across large period of time, and make some flame graphs on top of ClickHouse. We have system stack trace table. It is like connecting to ClickHouse, attaching with GDB, and showing some stack traces, so with debugger. But we have debugger embedded into ClickHouse, so you can run this query even now on your production servers. Don't worry, it will not disrupt your workload. You can run this query as frequently as you want. And my advice, if you want to entertain yourself on Friday night or on weekend, what to do? First, try to run your program. It is not just about ClickHouse, it is about everything you want to optimize. Run your program under strace and try to explain every line of output. If you will be able to explain, you will be able to optimize. Attach GDB to your program and show the stack traces from every thread. Run perf top on production. Look at the annotated disassembly. Figure out what exactly your code is doing. If you do some query and it runs 1 second, ask yourself, why not half a second? But if it runs 1 millisecond, don't stay still. Continue to ask yourself, why does it took a whole millisecond? A whole millisecond of time wasted. For what? You have to figure out, you have to measure, debug, profile. So always dig into details. Next advice. If you want to build a fast database, you cannot do this if you sit in your auditorium at University of Database Engineering, Minnesota. Is there such a university? I don't know. Probably not. Because if you do, your database will be fast only on paper or only on selected benchmarks, like TPC benchmarks. Many research academical databases are overly optimized on TPC benchmarks. They show exciting results, but these results never come to production. What to do instead? Always be close to production and optimize for real production workloads. And the more workloads, the better. More diverse workloads. And do quick iterations. Do one experiment, measure the result, do another experiment, and so on. How to do experiments? What about benchmarks? I like benchmarks. I even collect benchmarks. So some people collecting stamps. I am collecting benchmarks. But not everyone sharing my love to benchmarks. If you go to a website of some enterprise corporate database offering, you will see something like this. In their terms of conditions, you may not use the offerings in order to benchmark offerings or to build similar or competitive products or services. So they don't like benchmarks, probably for a reason. But I advise you, please do benchmarks. Don't prevent others from doing benchmarks. Always learn and improve. But don't do benchmarking. Instead, let your users do benchmarks and do the marketing for you. Always continue experimenting. If your system is already heavily optimized, like ClickHouse, it will be more and more hard to optimize further. But you still have to generate ideas. You still have to test every idea, even if only one idea out of hundreds will work. So I want to optimize my hash table. And I tried to optimize with CPU prefetch instructions. Did not work. I tried to do lookups with SIMD. Did not work. It worked in different systems in different contexts, but not in this particular context. I tried to calculate hash functions in instruction parallel way. I tried to use Robinhood algorithm, Swiss tables from Google. Did not work. They are great tables, but did not work specifically for group by in ClickHouse. I tried even to pre-allocate slightly more memory to avoid wraparound of hash table collision chains. Sounds complicated and it did not work. But at least one idea worked. Predicting hash table size to avoid unnecessary resizes. It worked, and we implemented this idea in ClickHouse, and we throw away 99 of other ideas, and this is normal. Another advice, do as many changes as you want. Rewrite code all the time. Don't be afraid of changes. Let automated continuous integration will do all the job of testing. So you must have functional tests, integrational tests with fuzzing. Fuzzing is must have in 2022. You have to use sanitizers if you write in C++. If you write in C++ and don't use sanitizers, your code is a trash. So you have to use sanitizers. Okay, and what else will help is automated performance regression testing. So you optimize your code, and continuous integration system will tell you, so you optimized this particular place 2 times. But every other query slowed down by 1%. So probably your optimization should not be approved. If you don't have performance regression testing, the history of performance tests, you may optimize one thing, optimize another thing, optimize third things, but in the result, your code will gradually slow down. About experiments. This slide I have added just 5 minutes, no, not 5 minutes, 30 minutes ago, because Maxim asked me to add this slide. It is about one of the most recent, one of the freshest optimizations inside ClickHouse. Inlining the comparison function for sorting with just-in-time compilation using LLVM. Without this optimization, 5 seconds. With optimization, 4 seconds. It was 5 and something, 4 and something. So 30% performance improvement, or 20%. I did not ask Maxim how this percentage is calculated, but pretty good. But it is just one of many, many different ideas. I asked Maxim, okay, I will copy paste this result to my presentation, but tell me please, how many experiments, how many ideas you have tried and failed? And he told me, so many, I did not even count, maybe hundreds of ideas, but this worked, and it matters. The results in continuous integration look like this. This is another optimization by ClickHouse contributor Raul Marin. He has optimized addition of nullable integers. And the automated tests showed 1.5 time performance improvement. Okay, probably next advice. Always test at scale. Test until everything breaks. Test on overload. You know that ClickHouse works fine, even on databases of 100 trillion records. This number is difficult to imagine. It is even bigger than the debt of United States, if I remember correctly, but I don't remember. But it is 10 and 14 zeros. But how we can test that it works? We cannot just load 100 petabytes of data for every test. But still, we can test at scale. One example. There is a dataset of Wikipedia page views statistics. This dataset is provided in public domain. It has 370 billion records, 1 billion time series from 7 years. And I took this dataset, I loaded it to ClickHouse. Then I loaded this dataset again. Then I loaded it again in 10 different ways. From single insert, from insert from multiple files in parallel, with insert from S3, with insert into merge tree, insert into replicated merge tree, with ClickHouse Keeper. I did it multiple times while testing our new ClickHouse Cloud. ClickHouse Cloud is a new service available in private preview. And now ClickHouse eats this dataset for breakfast. And it eats this dataset with 40 million records per second on insert. And I do this with every dataset I can find. Tell me if another dataset exists, and I will load it into ClickHouse. I will do benchmarks. I will do experiments. Do weird stuff. Don't worry, please. This is not me, but looks very similar to me. You will face common beliefs and misbeliefs. And you should always challenge these beliefs. So you may heard that ClickHouse probably not good at large binary objects. So believe it or not, you have to check. What I did is I just loaded 600 gigabytes of HTML pages into ClickHouse, and surprisingly, it went all right. Now I can say that maybe ClickHouse is all right at large blobs. So probably ClickHouse is not good at direct insert queries from JavaScript, from web pages. Imagine it looks like insanity. A user is loading web page, and this web page do insert query directly from front end, from the browser. You will never do it with MySQL. You will never do it with Postgres. You will do it probably from server-side code from Node.js. But I was very curious. What will happen if I do exactly this? And I did exactly this. I built a service on top of this idea and persuaded all my team to use this service. Pastebin service on top of ClickHouse. You can check pastilla.nl. What will happen if I will use URL table function to do 10 million HTTP requests in parallel? Probably it will explode. And yes, it exploded. But we fixed it, we cleaned it up, and now it works. There are more and more common beliefs. ClickHouse is probably not good as a key value database, as a streaming data processing system. Yes, ClickHouse is not Kafka, and this is for good. ClickHouse is not MongoDB, and this is also a good to know. We don't like to be like MongoDB. ClickHouse is not good for full text search because we are not like Elastic. And I am happy that we are not like Elastic. But please hold my beer or just read our roadmap for 2022. It is going to be interesting. What else? What is the most important? The most important for every database developer is to have fun. Always have fun. How to have fun? Do whatever you want, whatever, as long as you can make some observations and do conclusions and debunk illusions. One example. 1 week ago, I have loaded the first 1 trillion prime numbers into ClickHouse, into a table inside ClickHouse. For what? What is the reason? What is the application? But do I need any reason to have fun? I just want to do it. It's enough. No application of this idea. So I have written a shell script. It starts loading these prime numbers, and I go to sleep. Yes, my dreams were all right. I woke up only to find out that the disk on the server is full. So the load did not succeed. But after a few minutes, I attached external storage with S3 to ClickHouse and continue loading. And this way, I have tested the reliability of ClickHouse Keeper. Yes, it was a replicated database. Merge tree over object storage and replicated databases. So at least it had some applications. And to finalize, you see quite strange query. Do you recognize this code? What is it? Is it fast? What query is faster, this or this? Can you optimize it further? I will not answer to these questions. You have to try by yourself. I want you to also have fun. Don't miss it. So, how to write a fast database management system? You only have to use good algorithms in a good context. Dig into every detail, measure everything, be close to production, do benchmarks, do more benchmarks, never stop experimenting, test at scale, do weird stuff, and have fun. Get alive. Start contributing to ClickHouse. ClickHouse is open source. Be the part of our community. Okay, that's it. I hope you enjoyed. Ready to answer your questions.
Awesome. Thank you, Alexey. I just have to repeat, if a query runs in 1 millisecond, ask why it took a whole millisecond. I also want to be aware of time, and I know some people are going to have to drop. So before we get to questions, if there's questions, please drop them in the Q&A. Alexey and I will hang out and answer them. I want to say thank you to the team from Opensee. Thank you for joining us on this meetup. Thank you for sharing your story. Check out opensee.io and Opensee_IO on Twitter. You mentioned your hiring. I encourage those of you who are on this call or those of you who will watch this in the future to check that out. Guillaume's, to both of you, thank you immensely for joining us today. We appreciate it.
Thank you, Tyler. Thank you, everyone.
Awesome.
We don't hire only Guillaume in the company, by the way.
It's a good test, right? Are you a good fit for the company based on first name, right? Alexey may load the first trillion primes. We just look at first names.
Thank you, everyone.
Cheers. Thank you so much. All right. It looks like a question just rolled. Actually, it's a statement, but I'm going to share it with you, Alexey, because it's important. I don't think we'll have a life if we take all of your suggestions. The life will just be writing DBMSs. And then it said, by the way, this was the best presentation from Alexey so far. Yeah, shout out to that. That's I get the joy of working at ClickHouse. So I get to see a lot of good presentations, but this one for me is special. The next question is, does nested structures work fast enough? It says then usual columns created on demand. For example, this person has 10 columns and they're thinking about maybe should I replace all 10 with one nested? What would your gut be for that?
If you use just nested data structure with explicit subcolumns, explicit data types, it will work as fast, no difference at all. In very recent versions of ClickHouse, you can also use object data type. Object data type is also nested data structure, but dynamically with dynamic subcolumns. It will automatically derive the data types dynamically, and if it will derive the most precise data types, it will be also as fast as a strict schema. But sometimes it will make suboptimal choice. Like it will choose string where you can have IPv6. There is specific IPv6 data type inside ClickHouse. Or it will choose string, but you can have enum or low cardinality of string, and then it will be slower.
Excellent, that makes sense. And to call back to your presentation, I think the other assertion that would go along with that is, yeah, don't take our word for it. Try it on your set of data, and see what unique solution you are able to divine. Cool. It looks like that's the majority of the questions. By the way, if you didn't catch it earlier, there was a happy FizzBuzz reference that everyone should play with FizzBuzz at some point in their career. And if you aren't familiar with the count distinct problem and are interested in probabilistic cardinality estimators, hyperloglog is worth the read. I want to thank you. The world is slowly reopening. We're doing a virtual meetup because we sort of have to. We won't have to in perpetuity. We will be able to be in the same physical location as many of you. I'm Tyler at ClickHouse. If you're interested in speaking at a meetup, or I see Alexey, we'll get to it in a second. Interested in speaking at a meetup or hosting one, please feel free to reach out to Alexey or myself. And a question came in, so we'll address that. The question is, did the inserts from the webpage case hit the too many parts problem? ClickHouse generally is known to dislike lots of parallel short inserts.
Yes, ClickHouse is known to dislike many parallel short inserts, but specifically for this use case, we have introduced asynchronous inserts feature. And I did this experiment exactly to test asynchronous inserts on a real scenario.
Nice. Awesome. Well, we're at time. If you have other questions, find us on Twitter. Send me an email, send Alexey an email, join our community Slack, participate in Telegram, go to GitHub, participate in the community. We'll follow up with video when it's available, probably put it on the blog as well as on YouTube. But between now and when we see you again, to Alexey's point, test things and have fun doing it, because ultimately that's the only way to build a performance system or a healthy community. Cheers, everyone. Thanks so much.